Okay, so we can begin. Hello, everyone. Happy Tuesday. We are very glad to present another episode of Paleoperk Seminar, and we're very excited to have Antoine Champreux from Flinders University in Australia. And today, Antoine is going to speak to us about combining the fossil record and computer simulations to study the effects of climate change on South American ecosystems after the last ice age. For those of you who are new, we'll go over today's format of the seminar. So first, we'll have welcome and announcements, which is ongoing, followed by a talk, which will be approximately 30 minutes, which will be followed by a moderated question and answer session. And Antoine has very kindly agreed to stay with us for tea time. Tea time is an informal session where postdocs and PhD students are encouraged to join and have an informal conversation with our speaker and get to know their work more closely. Don't forget to send your questions via chat to the questions at PaleoPerks host, who today is Nina. A bit of housekeeping before we begin. PaleoPerks values the participation of all folks interested in the paleosciences. Please remember to abide by our code of conduct during today's seminar. You shouldn't be able to unmute yourself, but in case you do, please mute yourself for the duration of the talk. You can ask questions by chatting to the questions at PaleoPerks host or by using the raise hand function. If you face any technical issues, please contact the questions at PaleoPerks host. We have closed captions built in into Zoom. Use the CC button to show or hide them. Paleo Perks promotes and celebrates the work of uh, early career researchers. Please nominate an outstanding ECR. The link to the form will be dropped in the chat shortly. We also collect weekly feedback for collecting information on the demographic, which is completely optional and highly encouraged. The link to the chat, uh, the link to the form will be dropped in the chat shortly. Now, to introduce our today's speaker, Antoine Champreux. He did his bachelor's degree at Montpellier University in France. And then he completed his PhD at the Flinders University in Australia, and currently he is in France thinking about his next steps. Antoine, please take over.
Yeah, just trying to share my screen.
Yes.
uh, okay, can you see it?
Yep. Perfect.
Yeah, so hello everyone. I'm Antoine Champreux. I just completed my PhD at Flinders University in Adelaide, in Australia. So first of all, I would like to thank the PaleoPerks team for inviting me to present this talk today. And I've decided when I received the invitation to use this opportunity to present a brief summary of what I did during my PhD. So the title of the talk is combining the fossil record and computer simulations to study the effect of climate change on South American ecosystems after the last ice age. So first of all, to give you a bit of context, my PhD focused on the neotropical realm that includes South America, but also Central America. It's a complex place that overlaps the equator and the two tropics that has resulted in complex biome and ecosystem distributions from temperate forests to deserts and tropical forests. But in fact, what we see in today's landscapes have been strongly shaped by several ecosystem upheavals that occurred in the last 20,000 years, so just after the last glacial maximum during the Ice Age. In the last 20,000 years, so just before the Holocene, there has been temperature increase, a global temperature increase, but with some latitudinal differences. Here on this slide, you can see two graphs. representing the changes in temperature from 20,000 years ago to the onset of the Holocene. And what we see here is that the pattern of temperature increase are different in the northern hemisphere and in the southern hemisphere. With in the blue area, you can see the Bolling Hall Road in the northern hemisphere, with a sharp increase in temperature followed by a decrease, and then followed by the Younger Dryas. While in the same time, the temperature increase in the southern hemisphere was more gradual, with an interruption and even cooling during the Antarctic cold reversal. And during this period of deglaciation that lasted about 8 to 9,000 years, the neotropical realm was marked by several large-scale ecosystem upheavals that have affected strongly and that has lasting effect on the continent. This includes the fact that the continent was the last to be populated by our species, and we see a densification of human activities just after the last glacial maximum. We also see some megafauna extinction. To give a bit of number, this represents more than 80% of the species that went extinct just after the Antarctic cold reversal. Just to remind you, this is a period of cooling in the southern hemisphere just after, during the warming. And we also see some vegetation changes from the fossil records. Most of it includes increase in forest cover all over the continents. But in fact, the link between all these events are poorly known, notably due to the lack of quantification. So yeah, I just wanted to show you this picture from Julio Lacerda, representing the megafauna in the Pampas in the late Pleistocene. The ecosystems in South America, in some places, were looking a bit like what we know in Africa today, with large animals, large herbivores grazing in open landscapes, and also their large predator. But almost all of this disappeared just before the Holocene, so about 12,700 years ago. So I had two main questions in my PhD. The first one, could post-last glacial maximum climate changes have led to large-scale vegetation changes in the neotropical realm? And then, could such vegetation changes have facilitated megafauna extinctions? So I've decided to present this talk, to structure this talk following my 5 main chapters in my PhD thesis. So in the first one, it's about how to represent the diversity of ecosystems on a large scale in a synthetic and standard way. So I focus on the concept of biomes. In the second one, it's more a review of what we know from the fossil record about vegetation changes. Then the last 3 chapters focus more on vegetation simulations, and comparing it to paleo-vegetation records. And finally, I focused on megafauna extinction in the southern cone, where we found most of the megafauna fossils. So I will go chapter by chapter. The first one is called How to Map Biomes, Quantitative Comparison and Review of Biome Mapping Methods. So yeah, why I did this chapter, it can be a bit cryptic, because it's a bit not the main aim of my PhD. But in fact, when I started working on this PhD, on this project, the first thing I did was to try to know more about the distribution of ecosystem in the neotropical realm. And I was looking for a biome map. And finally, I found several ones, lots of biome maps. So these are 4 examples, and you see that there are some similarities, but there are 4 different biome maps on your screens with different biome distributions. So that's why I focused in the first chapter to study this concept of biome, just to know if we can use biomes to represent changes in past ecosystems. So I identified that there are three main families of biome mapping methods that differ by the data they use, the biome definitions, and also the methods to get the data. So we've got compilation biome maps, functional biome maps, and simulated biome maps. Compilation biome maps are compilation of regional maps. So these ones are tend to be very accepted by the community because it's very consistent with pre-existing maps. But the issue with this is that we combine maps with various biome definitions. So there is no uniform biome definition. And in fact, we map things without definition. So we don't really know what is mapped, but we map a synthesis of regional perceptions. So another way to map biomes is the functional biome maps. There, we use satellite imagery mainly, and we map the structural and functional attributes of the actual vegetation. So the advantage of this is that we map vegetation using a standard definition. But unfortunately, the information is mainly limited to what we can get from satellite data. And finally, the third way to map biomes is to use simulation, so simulated biomes. There, we map biome based on hypothesis on the relationship between vegetation and other drivers. Most of the time, it's based on the relationships between climate and vegetation that can be more or less complex depending on the biomes. There, the main advantage of this method is that we can test hypotheses, but the disadvantage is that we do not aim to represent the actual vegetation. So we have to be very careful when looking at such maps because some drivers of vegetation distribution are probably not considered. In fact, when we try to map, so this was for modern biome maps, and when we try to map past and future biomes, we can use the same approaches. So we can do a compilation of information from fossil record, from lots of different information. This is on your left, a map of the last glacial maximum biome map from Ray and Adams in 2001. We can also map the functional biome maps based on vegetation functional traits that we get from paleoproxies. For example, we can get the tree cover or the proportion of evergreen or deciduous plants. And finally, we can simulate past or future biome maps using past or what we know of past and or future climates. And if it's based on paleoclimate experiments at global scale, we can make global scale maps. Here on the example on your right, that's an example of a Miocene biome maps from Forest et al. In 2015. So in this chapter, I try to see spatially where do the map tend to disagree the most, because there are various number of biomes, geographical extent, and boundaries. So I developed a protocol to represent the agreement and disagreement between maps spatially. I compare these four biome maps that comes from the different approaches. And that's what I get. So I got a map where here in darker area, that's where we've got the higher agreement or the lower disagreements. And in the lighter area, that's the lower agreement or the higher disagreements. What we see here is that the higher agreement occurs mainly in equatorial forests and in tropical deserts. And in fact, when we look at the latitudinal pattern of this agreement, if we make an average, so that's the graph on your right, the surprise was that the higher agreement occurs almost exactly on the tropics and on the equator. So what I did then was to try to identify if there is a reason for this. And I found out that these areas of high agreements correspond well if you compare, so this map on the left to the map on the right that represents the fraction of habitat loss due to human land use. In darker areas that indicate that the areas have been strongly modified by human activities. And in fact, the higher agreements occur in places that have been the best preserved. So the equatorial forest and the desert, probably because it's very difficult to live there. So overall, I demonstrated that there are high rates of disagreement in some area with an heterogeneous pattern, with a strong effect of human activities. And finally, biomes are probably not the best tools because depending on the definition of biomes that we use, we'll have different results. So it's difficult to compare. So I've decided in the following parts of my PhD to focus more on direct measures, such as the variation of tree cover when I represent vegetation. So this chapter was published earlier this year in Ecological Monographs. So if you want more detail, I invite you to read it. So the next chapter is called Post-Last Glacial Maximum Vegetation Changes in the Neotropical Realm. That's a review of paleoenvironment records. The question was, what does the plant fossil record say about vegetation changes in the last 20,000 years? So that's a review. The aim was to summarize the changes in the various regions and to try maybe to identify the main drivers of vegetation of tree cover change mentioned in publications. So on this map, I've represented the distribution of the fossil vegetation records from the last glacial maximum in the neotropical realm. What is important here is that most of the records are pollen, but that's not only pollen. And some region like in southern USA or northern Mexico, it's mainly plant macrofossils due to the climate. There is also an heterogeneous pattern of distributions with some areas that are poorly investigated, such as the Amazon basin, while others, like Patagonia or the Atlantic coast, have very numerous records. So overall, there is a general increase. So yeah, sorry for the French. There is a general increase of the tree cover and changes of different natures. It's asynchronous among regions, but some regions remain stable. So for example, I will tell you about the Patagonia and Amazonia. So in Patagonia, that's the place where we found the higher number of records. So we've got a good idea of what happened. In fact, there is a gradual north to south expansion of nothofagus forest from the last glacial maximum to 7,000 years ago. But this occurs mainly in the Andes, while in other places, such as in the dry diagonal, it probably remained very open and so continuously stable during the whole period. In the Amazon basin, the story is a bit different. We only have 3 records that show different vegetation patterns. So the main hypothesis there, even if it's debated, is that during the last glacial maximum, the Amazon rainforest was very reduced, maybe fragmented. And then about 15,000 years ago, there is an increase in tree cover with the Amazon rainforest starting to look a bit like what it looks today. So in the next chapter, which is called The Response of Neotropical Tree Cover to Variation in Post-Last Glacial Maximum Climate and Atmospheric CO2, I tried to quantify the potential changes in vegetation after the last glacial maximum using computer simulation. And then I can compare it to the review I did in the previous chapter. So the general approach to simulate past vegetation was to use a dynamic global vegetation model called LPJ-GUESS that I combine with transient paleoclimate data from the Trace 21 paleoclimate experiments. And then from the vegetation simulation, I compared them with, for present day, with remote sensing data for modern tree cover, and for the past with paleovegetation records. In fact, I did 7 different simulations, 3 for the deglacial period, 3 for the Holocene, and 1 for present day. So just to give you the main concept of the model, LPJ-GUESS. So here we don't simulate all the plants. We just simulate a few plant functional types that are representative, that represent average species, that should represent the whole diversity of functional traits in the vegetation. And all the plant functional types, for example, you can have a tropical tree that is evergreen, another one that is deciduous. We represent grass or even shrubs. And all these plants will react differently to climate. And then it's a bit of kind of a virtual gardening where the model represents various physiological processes like photosynthesis, respiration, evapotranspiration, or carbon allometry. And all these plant functional types are in competition. And what we do is to divide the whole area into, with a grid, into small pixels, where we do individual and independent experiments for each location. And at the end, we can make the average results of this virtual gardening, so we can get a lot of information from the simulation, such as the tree cover that is of interest here. So this is the first result. If we compare modern tree covers, the simulated one, to the one from satellite that is on the left, you can see that there are the main trends of the distribution of forest is well represented, but there are also some big differences. And these differences, these anomalies, are either overestimation in red or underestimation of the tree cover by the model. So it means in the red areas, the model simulates too much trees if we compare it to the actual vegetation. And in fact, once again, when comparing it to the map of the effect of human activities, we can observe that it's a bit obvious that in the red areas where there are overestimation of the tree cover, it corresponds well to areas where human activities are very intense. So yeah, this is the same data showing that as you go to the right, that's an increase of habitat loss, so of human activity impact. And in fact, the overestimation is positively correlated to this anthropogenic habitat loss. But now, when we look at the past, we see that there is a general increase of forest cover all along the period from 30 to 44%. But most of the most visual changes occurred during the deglaciation period in the tropics. And also in Patagonia. So in the tropics, we see that the model simulates that the Amazon rainforest was much smaller. And then in the two following experiments, so at 15,000 years ago and 12,000 years ago, there is a southward displacement, a temporary southward displacement of the Amazon rainforest, bridging the Atlantic rainforest and the Amazon rainforest. And then when we look at the Holocene simulation, so the 3 next simulation, they are pretty similar to what we know today. So this means that most of the changes occurred during the deglacial period. Then when we look at the stability of each pixel across the 7 experiments, we observe that in the darker areas, that the pixels that change the most in terms of standard deviation, this represents for more than 20% of change in tree cover. This represents only 1/3 of the grid cell, meaning that most of the change in the neotropical realm occurred in 1/3 of the grid cells, while most other places only recorded a few changes. So overall, most changes occurred during the deglaciation. There is a general increase in tree cover, and most of it occurred in 1/3 of the area. In the next chapter, which is called Challenging Agreement between Simulated Post-Last Glacial Maximum Biome Changes and Pollen-Based Biome Reconstruction in the Neotropics, I tried to compare, based on the same simulations, I tried to compare the biomes, so the vegetation, simulated vegetation, with biomes from the model. So yeah, this translation from pollen records to biomes via pollen plant functional types has been done in 2009 by Marchand et al. Within the Biome 6000 project, that is a global project trying to do that for the whole world after the last glacial maximum, mid-Holocene, and present day. And in fact, we translate pollen types into pollen plant functional types, and biomes are combinations of pollen plant functional types. So what I did was to transform my model plant functional types that are different. So I translated them into the same plant functional types than the pollen. To get a combination of plant functional type from the model, but trying to use the same definition to be consistent, considering my first chapter regarding the biome concept. So this is the first result. So for the modern biome map on the right, that has some shared patterns with the modern biome map from Marchand et al. In 2009. And when we look at the past, so the last glacial maximum, the mid-Holocene, and the present, we see that there is an increase in temperate and tropical forests, a decrease in open landscapes, such as deserts, and that the main trends are in general agreement with the Biome 6000 results. But when we look at a local scale, meaning that when we look at each record location individually, the agreement is pretty low, meaning that even if it's like if we compare for each record, is it the right biome that is simulated? If we compare it in terms of class of tree cover, so something a bit larger, it's never very high. And if we look at the changes between two periods for different drivers, different factors, it's never very high neither. So meaning that the model is not able to reproduce what we observe at local scale, or that local scale record don't represent well the large picture. It's probably a matter of scales. In the next and last chapter, so climate-induced vegetation changes, I found that climate-induced vegetation changes alone fall short of explaining late Pleistocene megafauna extinctions in the southern cone. So this is about the second question of my PhD, trying to know if vegetation changes could have facilitated megafauna extinctions. So first, I estimated the pattern of megafauna extinctions using a probabilistic model based on radiocarbon age estimates. And I compared it with a simulation of vegetation only around this extinction time. So when we look at the megafauna data, megafauna age estimate, there are several taxa with reliable age estimates based on on geochronologist criteria. And in fact, most taxa went extinct just after the Antarctic cold reversal, so about 1 millennium before the start of the Holocene. And this happens for almost all taxa, but also whatever their diets. And then when I try to represent using a probabilistic model, the pattern of extinction spatially, the extinction is between 13,500 years ago and 12,000 years ago. And it differs depending on the places. But when we look at the uncertainties, in some places, it's very high. So in fact, even if we have an age of extinctions, the quantity of data is at the moment not enough to make sure that we have the overall picture and that we know when it went extinct. The only place where it seems to be kind of precise is around near Tierra del Fuego, so in the south of Patagonia, where the extinction is about 12,700 years ago. So now that we have the pattern of megafauna extinctions, I've simulated the vegetation changes from 15,000 years to 11,700 years ago. And around the extinction, we can observe that several characteristics of the vegetation have changed more than at other times. This includes, so we've got an increase in temperature after the Antarctic cold reversal. We've got an increase in the savanna area, a decrease of tree cover, and a general increase of shrub cover. So this is average for the whole southern cone. But in fact, the scale of these changes seems very low to explain the extinction of so much megafauna species. I looked also at the effect of the variation of sea level on the area available for megafauna. So there is a decrease of the emerged area by 36 meters during this period. But here again, it doesn't seem very huge. So it would be difficult to explain the extinction of megafauna just by this. But anyway, there are some changes in vegetation and in the total emerged area that could have facilitated megafauna extinctions. So overall, the extinction was just after the Antarctic cold reversal, with low timing uncertainties only in the south. It corresponds to some changes in vegetation, but the scale of vegetation changes is small. Thus, the climate-induced vegetation and sea level changes could have facilitated megafauna extinctions, but they are probably not the main cause. And there we can think about human activities, because when I was doing my PhD, so the big question is it climate, for example, via the increase of tree cover that decreases megafauna habitat, or is it human? And some other studies have shown that at this time of extinction, there is an increase of prehistoric stone tools specialized in large animal hunting. So we are not sure yet, but anyway, my PhD doesn't support the fact that vegetation would be the main driver of extinction. So now we are at the conclusion. So the first question was, could post-last glacial maximum climate change have led to large-scale vegetation changes in the neotropical realm? So we've seen that there are widespread spatial differences among biome maps. there is a gradual increase of tree cover, but with very different patterns among regions, affecting about a third of the areas. And the agreement between pollen and, if we go larger, between paleoproxies and simulation at large is good at large scale. So at large scale and the main trends, but it doesn't work at more local scales. And could such vegetation changes have facilitated megafauna extinctions? So yeah, maybe it could be a facilitation, but it was probably not the main cause. So we can think about the responsibility of humans, I would say once again. So yeah, I leave you with this picture again from Julio Lacerda. And yeah, maybe you have some questions. Thank you.
Thank you, Antoine. It was a great presentation, very interesting. I would like to remind our audience that you can send your questions to the questions that PaleoPerks host, or you can directly post them in the chat or raise your hand. Meanwhile, we have a few questions for you already, so we'll get to that. Our first question is from Karthik Sendur, and he is asking, how did you account for preservation bias in each of the South American sites for the pollen? That is, how did you standardize the data?
Yeah, okay. So what I did, I didn't really quantify the agreements. I don't know if it's a question, but I considered it when interpreting the data, and that was part of the discussion. But indeed, that's probably why it doesn't work between the fossil record and the simulation, because they work at very different scales. But what was interesting was to identify what was in common between in the messages between the fossil record and the simulations. So yeah, I don't know if it answers the question.
But I think, yeah, if Karthik has any follow-ups, he will ask us. But I think that is fair enough. So we have an anonymous question. Um, what sources of information were used to map global human land use, which led you to the conclusion that least human modification correlates with high agreement among the three biomaps?
Okay, so this is a map that has been made by Ellis et al. In 2012. So it accounts for human activities. So for human land use, so it's not my study. I just compared it to this data. It was mainly from agricultural activities. So it's an addition of the various sources of human land use. Yeah, sorry, I don't remember the fraction of everything, but yeah.
Yeah, okay. Thank you. We have another anonymous question. Can you comment on the impact of the unresolved subgrid processes in the LPJ guess model for the vegetation simulator?
Of the unresolved what? Sorry.
The unresolved subgrid processes.
I didn't understand
So
the
I
question.
think the question is asking your the model has a specified grid.
Yeah,
So what happens to the processes which happen at a smaller scale? The vegetation processes that happen at a smaller scale, do they impact the model, or are they being accounted for in the model? If you have any idea on that.
yeah, okay. So the grid we've got as input data, it's an average data for each place. Then within each grid cell, There are several experiments, so we make an average of this because there are some stochastic processes. But indeed, yeah, it's close to the first question finally, because here we represent something that is at very large scale, and we don't look at very local processes. So yeah, it's just yeah, it's another way to look at things.
Hmm. But that would have an impact on the simulated vegetation, right?
No.
Okay.
I'm not sure to that I understand that I
Okay.
understood the question, but yeah, we've got several subgrid processes that are simulated, like the competition between plants. Everything is virtual, so plants are in competitions within the model, and then at the end we get the simulated vegetation. Um, yeah,
Okay. Thank
yeah,
you.
I'm not sure to
Uh,
answer well.
so we have next question. Do you know if these post-LGM deglaciation trends in the study are similar to vegetation trends observed during previous deglaciations? Like how similar are the deglaciation trends of vegetation for
Ah,
other deglaciations?
yeah, so I'm not aware of previous simulation with that precision for previous deglaciations. So yeah, I think there is no study about that yet. Because before my PhD, there were some simulations already, but just for a few smaller places, not for that much periods. So yeah, it would be hard to compare it since I'm not sure it exists. But yeah, I'm not sure if it's the same because the climate was not the same. But yeah, there is no simulation, so it's difficult to compare. And even for the fossil record, I'm not sure that we've got a good enough coverage for the whole neotropical realm so we can compare it. So in
Hmm.
fact, we don't know, I would say.
Mm, yeah, that makes sense.
If
So
someone has the
Karthik,
answer to this, I would be happy to know it.
Karthik is asking, how would the agreement values between predicted and actual biomes slash tree cover have varied over time, especially as the magnitude of anthropogenic action has drastically increased over time?
Yes, so the question is a bit long. Can you
Yeah,
repeat it?
yes, you can also read it in the chat.
Ah,
I
yeah.
will reread it. How would the agreement values between predicted and actual biome trees have varied over time,
Uh,
especially when the magnitude of anthropogenic action has increased? So I guess he's asking how the agreement values of predicted biomes have increased as
yeah,
anthropogenic action has increased.
yeah, okay. So in fact, so the model doesn't consider anthropogenic action. And in fact, there is an increase. So I can go back to the slide because, yeah, maybe it was a bit quick. Yeah, so on the graph on the left, in red, that's it shows the increase of agreement for each location, by location agreement. So yeah, we've got an increase from less than 20% during the Ice Age and up to 40% for modern time. I didn't consider, yeah, probably without human action, it would be different for modern time. It could be higher, but yeah, I'm not sure. It depends on the distribution of the sites. So yeah, I didn't focus on this aspect.
Okay, thank you. We have, I think, an anonymous question. What do you think could be modified in the reconstruction method to get a higher agreement between the local pollen records and the global reconstruction of biomes?
Yeah, so one of the main difficulties when I did that was that the map that you can see here on the left is not like it's a drawing. So to calibrate the definition of the biomes, it was impossible to use the right reference. And since I wanted to use the same definition, the same biome definition, I had to have the distribution of the biome, not the full map. So I think maybe because I did it I could only do it visually. Um, if the Biome 6000 project was made with a biome map that is well georeferenced, I think maybe the agreement would be higher, or maybe not. So yeah, this was a difficulty, but I think this could be improved. Yeah, but again, because we have different definition of biomes, mapping biomes based on the same definition that we use for the pollen, mapping biomes at continental scale. I'm not even sure that it's possible because the criteria are not the same, and it would be difficult to reference for each place the composition of the pollen type. So yeah, that's a good question. And yeah, I think it's something we should work on in the coming years if we want to
Yeah,
compare.
that's very interesting and yeah, very challenging as well when you don't have like proper records that are made available. Um, so I guess we have one final question, which is asking, what do you see as the next steps for this work? Uh, Antoine?
Yes.
Yeah.
Ah,
Uh, so we
what I
have
see as
final.
the next steps for this work. Yeah, sorry. Um, um, there are various possibilities. I think one thing that I would do will be to focus on the effect of humans because in my whole PhD, I've seen humans as something that modifies ecosystem and as if we summarize it as a cause of disagreements most of the time between my simulation and the paleo environment proxies. So yeah, trying to consider the effects of humans on ecosystem in the past would be very interesting, I think. And also to try to combine the vegetation simulation with what we know of human activities at the time of extinctions. Um, yeah, I think it would be very informative.
Yeah,
So yeah.
it would result in a very interesting work. Well, thank you, Antoine, for giving an excellent talk and also answering our questions. I would like to thank everyone for joining us today. Next week, we are having a Paleo Pathways talk by Imran Ali from the Petrostat, a geoscience solution company. So see you on 5th November for those who you want to stick around for tea time and an informal conversation with our speaker. Uh, please do so. And the question for today's icebreaker round is, if you could live in an ice age, which one would you choose and why? Um, so we'll see everyone in 2 minutes. Take a break, walk around, and if you have paleo pets, feel free to bring them. Thank you.